Okay, good morning. So let us continue the lesson. If you remember last time, we stopped here, a theorem. Let A be a square matrix if B is the matrix that results if two rows or two columns of A are interchanged, then the determinant of this new matrix B is minus the determinant that you already have, yes? So determinant of A. So that's a very simple but very important theorem in the theory of determinants. So what does it mean? It means that, for example, this in the case of 2 by 2 determinants, it is extremely easy to understand, yes? So if I give you a 2 by 2 determinant, A, B, C, D, and if I interchange two, so let me call, let me write this matrix and call it matrix A. And let me define a matrix which is the same matrix unless that I interchange these two rows. The proof for this case is extremely simple. So what you just do, you want to calculate determinant of B. What happens? It becomes determinant C, D, A, B. And then, of course, by definition, you need to multiply these two, minus you multiply these two. But if you calculate determinant of A, which is A, B, C, D in this order, then you multiply A and D, and minus multiply these two. And then you can see that these C, B, and BC are the same, AD is the same. The only difference is that here BC comes first, AD comes second, here AD comes first, BC second. So this means that the determinant of B and the determinant of A are not equal, but they are opposite. So proving it in this very simple case is, of course, very simple. But the important thing is that this can be generalized to higher dimensions. So if you have 3 by 3 determinant, 4 by 4 determinant, that will work. Okay? Of course, what I want to describe here is the sketch of the proof, but the general proof also goes along these lines that I want to describe. To understand it easier, so let us try to talk about a 3 by 3 determinant. Okay, so for example, let us say that I have a determinant A, B, C, D, E, F, G, H, I. Okay? It doesn't matter if you interchange these two rows, or you interchange these two rows, or even if you interchange these two rows that are far away from each other. What happens is that the determinant picks up a minus sign. But to prove this, first, I want to show this is true if I take two adjacent rows and interchange them. Okay. For example, let me take these two adjacent rows and interchange them. So what happens? It becomes D, E, F, and A, B, C goes down, and then I have G, H, I. Yes? Now I want to show that this determinant is negative of that determinant. So how should I show that? Here, if I ask you to calculate this determinant, you can calculate it by expansion on the first row. So you write A, and you eliminate this column and that row, you get this block E, F, H, I. The next one, you remember, is negative, and then you remove this column and that row. You have this block left. And finally, you have C, the determinant of DE, GH. Yes? So this is the answer to this determinant. Okay, but now here, if I want to find that, of course I can also expand it on the first row, but I intentionally expand it on the second row, because I want to compare the result of this determinant with the previous one. So it is better to make it very similar to this. So instead of expanding this on the first row, I expand this on the second row. But what happens? For the second row, this is the second row first column. 2 plus 1 is odd. So you remember there is a negative sign assigned to it. So when this is negative sign, the next one is 2, 2. So 2 plus 2 is even, so you have to put a plus here. And then the next one is what? Negative. So when I start calculating this determinant by expanding on the second row, I start with A, but there is a minus sign there, so I put minus. And then I remove this row and that column. The block left for me is E, F, H, I. So this is interesting. You see, by this trick, you can immediately compare this term with the first term here. You see, that's exactly the same thing. Okay, and then I go to the next one. This is plus. And then I eliminate this row, column and that row. It becomes D, F, G, I. Yes? And then I go next one, minus C. I eliminate that row and that column. So D, E, G, H is left. Okay? So now you compare this result. You don't need to continue further. That is the whole point of this proof. So it doesn't matter if this is 4 by 4 determinant, I don't know, 10 by 10 determinant. When you interchange two rows, the goal is to do this. You will expand the determinant, the first determinant on the row, on one of those rows, and expand the interchange determinant on the same row when it is changed. And then you see that what happens, the terms are exactly the same, but the signs are correspondingly opposite. So this means that this determinant is not exactly equal to that determinant, but it is equal to the minus of that determinant. Yes? So that is not a good way of writing. Yeah. But this determinant is this number. This determinant is the same number multiplied by an overall minus sign. So this means that if I call this x, if I call this y, then I realize that y is negative of x. Okay. This is the sketch of the proof, which of course works, and I hope that you agree with me if you make it 4 by 4. So let us check it another way. For example, let us interchange these two rows this time, okay, and generate a new determinant. Let me call this z. This time, I have this determinant, but let us decide to interchange this row with that row, okay. That is a little bit different. So let me change the idea. So that's not the, because I don't want to prove it case by case. But what do you think will, how can I prove that this will also give me the same result? So here, I hope that I could convince you, if you take two adjacent rows, okay, and interchange them, the new determinant is minus the previous determinant, if the rows are adjacent. But the question is that what happens if the rows are not adjacent? Because the theorem is still asserting that even if the rows are not adjacent, the rule will work. But why do you think it will work? So what was the take-home lesson from here? This lesson tells you, this sketch of the proof shows you, if you choose two adjacent rows and interchange them, the new determinant is opposite to the previous determinant, if the rows are adjacent. But my goal is to show you, not from scratch again, because I want to think about how can I generalize my argument to higher dimensions and for any rows. My question is that, why do you think, if we take this one for granted, that if I interchange adjacent rows, I will pick up a minus sign, just using this argument, I want to tell me why, if I interchange this with that one, even though if they are not adjacent, the rule still applies. Yes?
I just wanted to ask a separate question. They have to be adjacent, you said?
No.
They don't have to be adjacent?
No, in the main theorem, even if they are not adjacent, the theorem is valid.
Oh, okay.
But the proof that I showed here is only if the rows are adjacent.
Oh, okay.
And that is important because I want you to see the obstacle. So if you say that, okay, let us use this idea and let me interchange the first row and the third row. So GHI goes up, D, E, F, ABC goes down here. If I ask you to show that the determinant of this is negative of this determinant, how do you prove it? If you understood what I said for the adjacent rows, I want you to understand the same reasoning will not work in this case. So I need another proof. So let us say I want to follow the same thing. So let me call it Z. Do you remember? So let me just review this. I have two determinants. The difference is that in this determinant, these two adjacent rows are interchanged. And by this kind of argument, I was able to convince you that the new determinant is minus the previous determinant. Yes? What I did, I expanded this one on one of these rows, and I expanded this one on the same row after being interchanged. And then immediately it becomes clear that one of them is the negative of the other. Okay, now we want to do the same thing here. If you want to follow exactly the same logic, it's good. But if it doesn't work, if it works, we are lucky. If it doesn't work, we have to change our strategy. I want you to feel that this reasoning probably will not work here. Why? What do you suggest here? You try to expand this on this row. So this is 3, 1, so it is positive, because 3 plus 1 is E. The next one definitely becomes negative, the next one becomes positive. And if I expand this on that, this one and that one are gone, this block is left. Yes? And if you want, you can continue, minus B, and then you just draw that one, G, I, D, F is left. And then finally, if I put C, I eliminate this, G, H, D, E is left. Yes? But you see, there is no easy way to compare this with the previous one. Yes? Because the blocks are different. So even though these coefficients are exactly the same, they are comparable, but the blocks appearing in this way are not the same blocks that I have now. In the previous case, when they are adjacent, I produced the same coefficients and the same blocks, which was easy to compare them. Yes? But in this case, if I want to follow the same strategy, then there is no easy way to compare this one. Of course, at the end, you will get the correct result because another mathematician have already proven that. But I want you to understand that this strategy that I used in the previous case for adjacent rows will not work here. Okay. Now, the question is that this might be the case that this theorem is only valid for adjacent rows, or if it is valid for non-adjacent rows, the same reasoning that I used for adjacent rows will not work for non-adjacent rows. Is the idea clear? Okay. Now I'm asking you, do you have any idea how can I prove this case? Don't say that I can calculate. Of course you can calculate, but try to think about 100 by 100 determinants. Yes? Yes.
You can flip the first and second row, and then you flip the second and third row, and then you can do one more flip with the first row.
Yeah, that is the strategy. So what we do, I want to prove that Z is minus X. Okay? So let us say something. So you start from, this is by the way very important thing, yes? So G, H, I, D, E, F, A, B, C. Okay, from the previous one, I know that if I interchange adjacent rows, the determinant will pick up a minus sign. Yes? Okay. So what I do, I interchange these two. Okay? So that's important to understand what is going on. So I interchange these two. So what happens? A, B, C goes up, D, E, F goes down, and G, H, I is here. So, what is the relation between these two determinants?
The second one is a negative.
Yes, there's a minus. Yes, because these two rows are adjacent. I interchange them. According to what I showed for adjacent rows, I am allowed to put a minus sign. Yes? But now what I do, I again interchange these adjacent rows. Yes? So what happens? This time, it becomes ABC, GHI, and DEF. Do you agree that I don't need any minus sign anymore there?
Yes.
Because I pick another minus sign which cancels that one. Yes? And then what happens? I interchange these two once more. Yes, what happens? It goes here minus A, B, C, D, E, F, G, H, I. Yes? So then compare the first one with the last one. So you see that this is also valid. So even though I interchange these two rows which are not adjacent, but still I have my minus sign there. So this is important. What do you think is crucial? Because sometimes in the middle of the way, I have a positive sign. But I'm claiming that I will always and always end up with a minus sign at the end. It is not that trivial. You have to convince yourself that it's the case. So what does it mean? It means that always I need odd number of interchanges to do this. Because if I have even a number of interchanges to do that, then I will end up with a positive sign. But if the theorem is supposed to work, the only thing that matters to me now is to show that in every general case, if I want to do it by adjacent interchanging, I will need only odd number of interchanges, not even. Is that clear? Yes?
Sure.
So how should I convince myself? By the way, this is the proof, but you need to write it in a little bit of structured way. Okay. So why do you think this is always the case that I need an odd number of permutations, this odd number of interchanges to change one of them to the other one if they are not adjacent? So for example, let us say I have row 1, yes, row 2, row 3, and row 4. Let's make it a little bit bigger, okay, row 5. Okay. So, assume that you want to go from this sequence to this sequence. I don't know, for example, let us interchange 1 and 4. Yes, so let me put 4 there, and then 2 and 3, I don't change it. I put 1 here, and I put 5 here. Okay, so how many interchanges of adjacent numbers you need to change this sequence to that sequence? I want to convince yourself that every sequence can be changed to this sequence by odd number of interchanges. So for example here, what do you think I do? I want to interchange only adjacent ones. And by adjacent ones, what do I want to do? Is it easy to understand or not? How many interchanges I need to go from here to here? Because you want to bring 4 in the first location and move 1 to the 4th location, and you're only allowed to interchange the adjacent ones. Okay, if you understand it correctly, the claim is that no matter how these sequences are written, you need exactly odd number of interchanges, adjacent interchanges. So let us do one of them. For example, if you want to do this, what do you do?
Maybe you start with interchanging 1 and 2.
Yeah, don't be optimal. So I put 2 here, 1 here, and then 3 here, 4 here, and 5 here. Yes. So this is one interchange, and then
maybe 3 and 4.
Let us do them in order, okay? Not to confuse ourselves. So let me just, because I want to have a pattern at the end. So 3, 1, yes, and 4 and 5, yes? And then what I can do?
1 and 4.
Oh, I can choose 1 and 4, change 1 and 4. Okay, and then
3 and 4.
3 and 4. And then
2 and 4.
2 and 4. Yes? So how many steps I did? 1, 2, 3, 4, and 5. And the 5 is odd. Okay, so the only thing that remains to prove, you need to convince it yourself, that it doesn't matter how long this sequence is and which ones are interchanged. If I want to follow this rule, I need to do it only, I can't do it in odd number of steps. Okay? And if you can do that, then you have the proof of this theorem in its full generality. But do you have a simple argument why we can do that? You don't need to think about optimal way, because it doesn't matter if you repeat this process wrongly several times. Yes, every time you pick up a minus sign. So is that clear that we can do it in odd number of ways? Not that the best way to do it is the odd number of ways. I don't know about that. Might be the best one is also. Yeah, I think the best one is also odd. But that is a deeper theorem. Okay, that's a deeper theorem in abstract algebra. That if it is done in an odd way, even if you want to optimize it, the parity, oddness or evenness will not change. Okay, yes.
Can you explain again? Why the negative of x if it only changed once?
Oh, because I calculated them.
Yeah.
As by the definition of the determinant, but when I wanted to calculate this determinant, I expanded on the first row, and when I did that interchange, now this row is sitting in the second row, and of course I could expand again on the first row, but I am allowed to expand on the second row. When I expanded on the second row, I see more or less the same combination. If you compare term by term, you see that they are exactly the same unless the sign is changed.
And since it would only changed once, the rule applies.
No, this one is negative of that one.
Yeah.
This one is negative of that one, and this one is negative of that one. So this means that these two numbers are opposite because each term is the negative of the previous term. Yeah, so that one was the idea. But do you think we can have a good argument that this can only be done in odd number of ways? Or at least, not only on odd, so it can be done on odd number of ways. So for example, let us say that you have this sequence 1, 2, and then you reach to I minus, let me write it not hard. So you reach to some point I, and then you continue your list, you reach to J, and you continue your list, you reach to N. Okay? And then you want to interchange these two numbers. So it means that you keep everything the same, but you just interchange these two numbers and everything in your list is the same. So you need to convince yourself that from here to here, if I want to use an interchange between adjacent numbers, I can do it in odd number of ways. Is that understandable?
Yes.
Okay, but do you think we can prove it? So do you have any? Yes, you should think about it. It's not hard, by the way. Even I don't know. We need to think. Yes. So we want to interchange. The way that you mentioned is correct. So we interchange J with the previous one, and interchange again, so that J reaches to I. But then when J reaches to I is in the next position. So we have to start interchanging so that moving J to the other one. Okay. So how do you think we can organize this? Let us count how many interchanges you need to go here. So let us say that j is larger than I, so let us say that j is equal to I plus a number k. K steps forward, yes? Okay, so how many steps do you need to take j and move it here? So what does it mean? This means that the first number is I, the second number is I plus 1, the next one is I plus 2, and then you continue. When you reach to j, it means that you have reached to I plus k. Yes? What is the previous one? It is I plus k minus 1. Okay? So how many interchanges you need? Yes? One interchange, do you agree? Then the second one, and then you do it third, I don't know how many times you need, and then finally you need to do this. Can you count this? It shouldn't be hard, do you agree with me? It shouldn't be hard. So how many of these operations I need?
I plus k.
So how many numbers are sitting here? K minus 1. Yes, there are k minus 1 here. So I do one interchange, yes, so now it is here. Another interchange goes here, another interchange goes here, another interchange goes here. So how many interchanges I have done? K minus 1 till now, but I need one interchange to take it here. So how many interchanges I did?
K.
K, yes? Now what is the situation now? The situation is that I plus k is now sitting here, yes? I is sitting here, and then I plus 2 is sitting here, is that right? No, I plus 1, yes, what we did, so we changed that here, so interchange that. So I plus k is now sitting here, I is here. Okay, can you tell me what is the next one?
I plus 2.
I plus 2, and then we continue up to I plus k minus 1.
Yeah.
Yes? So this is my list. Okay? But now I want to take I and put it after that. So how many interchanges I need? This time I need k minus 1 operations. And in total, how many operations you need?
2k.
2k minus 1. But 2k minus 1 is even always an odd number. Okay? So that's good. So it is not hard, even though I did a little bit presented in a bad way, but I think it's understandable. So you just need to count the number of ways that you can do that. Is that clear? Okay. So this is exactly what is going on in the proof, but you just need to write it a little bit formal to have the rigorous proof of it. But using it is extremely simple. So whenever you see two rows are interchanged or two columns are interchanged, the proof for the columns goes exactly the same way. Two columns are interchanged, then what you get is that these determinants are related together like this. Okay. There is another theorem which is very important. If two rows or two columns of a square matrix are identical, then the determinant of the matrix is 0. It's a very good and handy theorem. Yes? Why do you think it is the case? So what is it telling you? It's telling you that if you want to calculate, for example, this determinant, 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12, and then 1, 2, 3, 4 again. Yes? If you have two identical rows or two identical columns, the determinant without any calculation, no matter how big this is, the answer is 0. So, why do you think this is the case? So you see, I just wrote the 4x4 determinant because it is time consuming if you really want to calculate that. But I am sticking to this rule that I am repeating two rows, identical rows. I am claiming that I don't need the calculation at all. The determinant is exactly 0. Why do you think this is the case? You should be able to tell me why. It's a very handy theorem, so it doesn't matter if you have very, very big determinant. If you detect two identical rows or two identical columns, don't calculate it, the answer will be 0. Why do you think this is the case? My hint is to use the theorem that we just proved.
If you interchange them, then it technically becomes another matrix. That becomes negative.
Of itself, but in the other hand, it doesn't change at all.
Yeah.
So the only number which is equal to the negative of itself is 0. So what Tino is mentioning is completely correct. Let us assume that we don't know it is 0. Let us call it x. And we want to prove that x is equal to 0. Okay? Okay. But now, what I do, I interchange these two rows. So 1, 2, 3, 4 goes up, 1, 2, 3, 4 goes down, and then I repeat everything else. Yes? Okay. On the one hand, so I interchange the rows. So on the one hand, I haven't changed anything, because you see this is exactly the same thing here. So on the one hand, x and y are equal. On the other hand, based on the theorem that we proved, they have to be opposite. So it means that if I add these two, this means 2x is 0. If 2x is 0, x itself is also 0. So that is a very handy tool in our hands. So if you know that determinants have two identical rows or two identical columns, the answer is immediately 0. We can also do more than that. So for example, if I say 1, 2, 3, and if I say 4, 5, 6, and then I write -7, -14, -21. What is the answer to this determinant rather immediately? This is something you need to remember from the previous session. The answer to this is also 0, but why? Because, do you remember what we had in the previous? You can factor a number from a row or a column. Okay, so what can I do here? I can factor -7 out from only the last row. You see, remember, that was the main point, don't get confused. In matrices, if you want to pull out a number, you have to divide every entry by that number. But in a determinant, if you want to pull out a number, you decide yourself which column or which row I want to divide by that number. So I decide to do that because you will see that with the help of this new theorem, what happens? It becomes exactly that one. So but after I factor -7 out, I will have two identical rows. So this becomes -7 multiplied by, but I realize that this is just 0, so the product is again 0. Okay, yes?
How does negative? Oh, sorry, it's -21.
Yes, yes.
Okay. I saw it as -2.
Yes?
Okay.
So if you have a determinant so that one row is a multiple of the other row, or a column is a multiple of the other column, the determinant is again 0, so you don't need to calculate it. So these are handy theorems that I want you to know about them. This is also an extremely important theorem, so let us mention it here. So let A be a matrix, a square matrix, if B is the matrix that results when a multiple of one row or column is added to another row or column, then the determinants are exactly the same. Okay, so what does it mean? So let us just check it for the 2 by 2 determinant. So for example, let me give you this matrix A to be A, B, C, D, and let us decide to add 2 times of this row to the next row. So let me keep the first row the same, but let us say I multiply every entry on the first row by any number you like, say 2, and add them correspondingly to the next row. So for example, I add 2a to the next row, and I add 2b to the next row. What is this theorem claiming is that in general case, even if they are higher dimensions, the determinant of these two matrices are identical. They are exactly the same. So let us check it, for example, for the case, a simple case that we have here. So what can we do? Of course, we know what is the determinant of A, because this is extremely simple to calculate. It's AD minus BC. Let me calculate determinant of B. So how should I calculate it? I have to multiply this by that, minus multiply this by that. And then what happens, if I expand that, and then you see this term is cancelled, and you get AD minus BC, and which is exactly equal to the determinant of A. Okay? But of course, you might say this is a coincidence. I agree with you, because this is the 2 by 2 determinant is so simple that you might say that, okay, simplicity causes this. Yes? But if we go to higher dimensions and different higher dimensions, this might not be true. I agree with you, so that's not trivial. That if I do it even for any, for example, if I give you this determinant A, B, C, D, E, F, G, H, I, so I can keep this column and that column, for example, the same. Then I decide to add 5 times of this column to the middle column. So this becomes 5b plus 5c, e plus 5f, and h plus 5i. So this theorem claims that without having to calculate these two determinants, actually this is true. That this determinant is equal to this one. So you are allowed to add a multiple of a column to another column, or you are allowed to add a multiple of one row to another row without affecting the result. Why do you think this is the case? For example, can you justify why these two should be equal? Because if you can justify this, the general proof is also the same thing. Very similar to the same thing. But can you tell me why do you think this is true? For example, let us start from the right-hand side. We want to convince ourselves that I can somehow, without expansion, because if you want to expand, then it means that you don't have a good proof for higher dimensions, okay? So without expansion, in the sense that, of course, I want to use the expansion theorem somehow, but I don't want to expand it until the very end to compare the final results, okay? So let us start expansion on the middle column, that this change has already happened. So what do? So here, this is the first row and the second column. So 1 and 2 becomes odd, so it has a minus sign here. But the next one is positive, the next one is negative. So if I start expansion on this column, you should be able to tell me. So what do you think I will write first? I want to expand this right-hand side on the middle column. So what do I write here first? Yes?
Is it b plus 5c?
No, a minus sign there. So it's minus b plus 5c. And then what do? I put a 2 by 2 determinant. What is that 2 by 2 determinant? I eliminate this column and I eliminate this row. I will have this block df gi. Yes? Then I go to the next one, but the sign is positive, so it becomes e plus 5f. And then what happens? I will have that block ACGI. And the next one is again negative. and then I eliminate that row and column. So what is left for me is A, C, D, F. Do you agree? Yes, do you agree that this is the right hand side? Okay, imagine I am expanding, but only the first part. I will not start expansion new determinants anymore. Because if my proof is based on expansion of new determinants, then it becomes harder and harder when I go to higher dimensions. But I want to keep it like this. Do you have any idea what to do now? The goal is to reach to this side. Okay, I can pause a little bit. I want you to do, let me do the first step myself. I take this one without expansion and multiply it inside. So this becomes minus B, the determinant of D, F, G, I. Yes? But there is another one, minus 5C. So if you don't mind, let me write that one here. Intentionally, I am doing it. So let me write this one, instead of putting it next to it, let me write it here. It's minus 5C, D, F, G, I. So if I expand that, I'm not expanding the determinant, be careful. I'm just doing simple algebra. I'm just multiplying this number in. I will get these two, yes? And then I will do the same thing here. So what do I get? One of them I write here up, and one of them I write here. The same thing for the last one. Okay. Now, of course, I need to put, so this means that in principle, this continues up to here, yes? Okay, now why do you think this is a good way of doing things? What do you think will be my goal of collecting the terms in this way? To put these three terms next to each other and to put these three terms next to each other. In other words, can you tell me what can I write instead of this first one?
Is it not the same as the determinant of the left-hand side?
Yes, but expanded on the middle column. Do you agree? So if I ask you to expand this determinant on the middle column, you will exactly get this one. Is that right? Yes. So it becomes equal to the determinant of A, B, C, D, E, F, G, H, I. Yes? But plus, let me factor a minus 5 out from here, or let me factor a positive 5 from here, okay? And then what is left for me is minus C, D, F, G, I, plus F. So if you answer this question, it means that you are completely following what I'm saying, yes? Yes? So what I did, I followed what Gustav mentioned. I hope that everyone agrees what is here is exactly this determinant, yes? Because if you start expanding this determinant on the second column, you really get exactly this expression. But now, between all these, I decided to factor a 5 out, rather than minus 5, and I am left with a similar combination here, but with a slight difference. But now, can you tell me, what can I write instead of this guy?
Is the determinant of the left-hand side, but on the right column? Yeah.
No, not on the right column.
On
Is
the
it?
CFI column.
Yes, on the CFI column. Yes, is that right? Let me see.
No, it's a
No, it is not. It is not, because that was surprising for me. If you expand on this determinant, what will happen? You will have, what is the sign for here? It is positive.
Yeah.
So you write C. Positive is not a problem. We can fix it later. But the problem is that when I eliminate this, what do I get? I do not get that block. We cannot tamper with blocks because blocks can be complicated. Yes. If I eliminate this row and that column, what will happen? this becomes DEGH.
Yeah.
C is no problem, I can fix it by minus sign, but this is not something I can fix in general when I am going to higher dimensions. So what you answered is not completely correct. But think better. You can still write something for that, what I put in this orange curve. Concentrate on the blocks rather than the coefficients.
The blocks are the same.
Yeah, the blocks are the same. So it means it is not an expansion on the third column. The reason that you said a third column because you were concentrated on the coefficients. But my advice is to concentrate on the blocks and write something. I just want to see who can solve that problem. It's extremely simple, by the way, not hard. So I copy and paste this one, you think about it. I can also give you a hint. That is a 3 by 3 determinant. Remember, the blocks are the same, but the coefficients are C, F, and I. What does it mean?
Maybe they interchange the second and the third column.
No, it doesn't work. It's simpler than that. The blocks are the same. The coefficients should be C, F, and I. I'm just telling you the answer. Yes.
You just change the middle row to C, F, and I.
Yes. Let us just do that. So I keep A, D, and G the same. In the middle one, instead of having B, E, and H, I will have the same C, F, and I. But in the second, third row, C, F, and I. Yes? If you don't believe, let us check. I am claiming that what is written here is the expansion of this determinant on the middle column.
Sure.
Yes, why is that? Because you put a minus C and you eliminate these two, you will have the same block. And then you go to the next one, you put F here, you eliminate this one, you will have the same block. And then you do that. I hope that I could I could convince you that this is correct. But now this is 0 because of the previous problem, because these have two identical columns. Yes, so this becomes 0, and then what is left for me is just A, B, C, D, E, F, G, I, and G, H, and I. Yes, it's a very beautiful proof, but I just want to tell you that it is. I hope that you agree with me. Regardless of how the matrix, how big the matrix is, I can follow the same argument. This argument is not hard because it would be hard. It would have been hard if I am supposed to calculate these smaller blocks, but I'm not calculating the smaller blocks, I'm just comparing the blocks. So it is doable even if I go to higher orders of matrices. Yes? Is that clear? So yeah, this is the proof. I mean, the beauty is actually in the proof, of course, but you need to be able to use it effectively. Is that clear? Okay. By the way, this also brings you some ease, some comfort in calculating the determinants. Yes? For example, let us just do this exercise. Consider the following determinant. Determine the value of this determinant by reducing it to an upper triangular matrix. Let me mention what do I mean by that. Because, of course, you don't need to do it. You know how to expand this determinant, but the way that we learn is not very efficient. Yes? Okay, so let us try to check this idea. Okay, so the determinant is this. We want to calculate the determinant 3, 5 minus 2, 6, and then I have 1, 2, minus 1, and 1, and then I have 2, 4, 1, and 5, and then I have 3, 7, 5, and 3. So hopefully, because this is a little bit, you need to learn this method that I'm describing systematically, but I don't want to confuse you with that. I just want you to see one simple example of how can I apply this theorem over and over again, okay? And of course other theorems. So what my goal, it is mentioned to put this into an upper triangular form. Why do you think it's good? Because if I have an upper triangular matrix, calculating the determinant is extremely simple. You just need to multiply the entries on the main diagonal. Okay? So let me just, please follow me. I don't want you to learn this systematically, but I want you to feel how I'm using this theorem. Okay, if I want to make it upper triangular, so what I need to do, I need to have this kind of determinant. That I have some numbers here, but everything below that should be 0. That's the goal, yes? But for example, I want to avoid fractions. So this is, let me interchange these two. You will see why this is good. But if I interchange these two, what should I do? I have to pick up a minus sign, yes? So it becomes, you might say why I am doing this, but be patient, you will see why. Okay? I don't want to teach this systematically, but I want you to see one example at least. And then I will copy and paste everything else. 2, 4, 1, and 5, and then 3, 7, 5, and 3. So I hope that you follow me that what I have done is valid. I interchanged 2 rows, and then I picked up a minus. So, but now I want to use this theorem. Remember, my goal is to make everything below 0, but in a valid way, yes? Because I want to make it an upper triangular determinant. Okay, so this is the algorithm. You need to use this entry to get rid of these 3. Okay, so how? For example, I pick minus sign here. I keep the first row the same, but I add minus 3 times of this row to that row. Do I change the determinant? According to what we learned, no. If you add a multiple of a row to another row, even though the entries in general will change, but the determinant will be left unaffected. Okay, so what I do, I take this one and in my head, because if you want to write down everything, it would be really time consuming. And the computers are very good in these calculations. So that is why it's a more efficient way of calculating determinants. Okay? So if I just multiply in my head by minus 3, I am not focusing on other. I just focus to get rid of this 3 here because I want to make it 0. Of course, I will change these entries, but they are not important if you follow this algorithm. So you multiply this by minus sign and add it here. So let us just do it in our head. Do you agree? The first one becomes 0. The next one becomes minus 1, yes? The next one becomes positive 1. The next one becomes 3. Do you agree? In principle, I can rewrite the second and the third and the fourth column and then repeat the process once more. But let us imagine I did that. Then I will take this one and multiply it by minus 2 and add it here. Because I also want to get rid of 2. So what happens? This also becomes 0. Minus 2 times plus this one is also accidentally 0, even better. And I multiply this by minus 2 and add it here, it becomes positive 3. And I multiply it by minus 2 and add it here, it becomes 3. And I also want to get rid of this 3. So I multiply this by minus 3 and add it here. So it becomes 0, and it becomes 1, and it becomes 8, and it becomes 0. First of all, do you agree with my calculations? Yes? So I got rid of these things. So unfortunately, I am left with these 2. I want to make those also 0. Okay. Making this 0 is not hard. Can you suggest something? So after doing the first one, you need to concentrate here and use this to kill this. Okay? So it is just simple to add this one to this one. Multiply this by 1, which is nothing, and add it here. It will not affect the determinant, so it becomes minus 1, 2, minus 1, 1, and then you have 0, minus 1, 1, and 3, and then I keep it the same, 0, 0. By the way, if you don't mind, let me factor a 3 out to make these numbers smaller, and then 0, 0, 1, 1. And then here, I am adding this row to this row. So this becomes 0, again 0, which is good, and the next one becomes 9, and the next one becomes 0. Yes? But still, it is not an upper triangular matrix. The only problem is here. So do you have any suggestion for me to get rid of that 9 as well? It's not hard. I want to get rid, do you understand that? I want to have an upper triangular matrix. So it means below this line, everything should be 0. I managed to make all of them almost 0 except that 9. So how can I make that 9 equal to 0 now? Yes?
When you added those rows together, why is the 0 in the corner left? The 3 became minus 3, right? And then it should
Okay, thank you very much for fixing that. Which one I did? I added this one to that one, yes? So that is not 0, that is 3. But of course, yes, you are right. We have to write it 3. But that's not a big problem for me now, because I don't care about this, but I care about 9. Okay? So what do you think I will do now? I want to get rid of this 9 by this operation, multiplying a row by a number and add it to the next row, to the other row. But the motive is I want to get rid of this 9. Which row do you think it will be good? Because you might say that I will multiply the first row by 9 and add it here. Of course you get rid of this one, but you make trouble here again. Because if you multiply it by 9 and add it here, this which was already 0 now becomes 9. It becomes my new problem, okay? So you need to do it in a way that you are not changing these, that you have tried hard to fix it, but you get rid of that, yes?
third row.
The third row, yes. So that's the whole point. The algorithm tells you first, concentrate on this and try using this, kill everything below it. And then after this is done, concentrate on this one. Don't forget about what is above. Try to use this to kill whatever is below. And then when it is done, concentrate on the next one and try to use this to kill whatever is below, and that's exactly what you said. So I multiply this by minus 9 and add it here. Yes? So what happens now? So remember, I have a minus 3 outside my determinant, so I have to copy. So I copy and paste the first 3 rows. 1, 2, minus 1, 1. 0, minus 1, 1, 3, and then I have 0, 0, 1, and 1. And as you said, I multiply this by minus 9 in my head and add it here. If I multiply this by minus 9, it becomes 0. When I add it here, it doesn't change anything. So it doesn't ruin my effort, yes, that I have done so far. The same thing here, it will not change, but when I multiply this by minus 9 and add it here, it becomes 0. When I multiply this by minus 9 and add it here, it becomes minus 6. Now, is my determinant ready and it's upper triangular? Yes?
Yes.
So if I want to calculate this determinant, this is the product of these numbers. I have also a minus 3 out. So I have 1 times minus 1 times 1 times minus 6. And if you calculate this, so this becomes positive 3, it's minus 18. Yes? It turns out that you can prove that if you write an algorithm follows this, or if you write an algorithm follows the first definition, this is more efficient than the other one. So if you, I think the best way to calculate determinant is another algorithm that if I give you a matrix, you write it as LU. It's possible under some circumstances to decompose a given square matrix as a product of a lower triangular matrix and upper triangular matrix. Okay? And then you can calculate these determinants simply, and there is a theorem connecting the determinant of the product to the product of determinants. Okay, so that's the way usually applications use to calculate determinants much more efficiently. So I don't want to focus on this one, but I just want you to see that how you can use this theorem several times to be able to calculate this determinant. So you are not, this is for humans, it doesn't matter that much because if this increases, this is also hard for us. But this is an algorithm, you can write the code for it and then use it to calculate determinants, okay? Okay, let me solve one more problem, and then there is some theorems left. We will continue later. Okay. So this is also a famous determinant. Okay. So x1 is a number, a real number. x2 is also a real number. x3 is also a real number. So on the first column you have 1, 1, 1. On the second column you have x2, x sub 1, x sub 2, x sub 3, and on the third column you have the squares of those. We want to determine this determinant by row reducing it. This process is row reduction, okay, to an upper triangular matrix. Okay, so we can do that. So how do you think I will do it? So this is also good. So I have 1, 1, 1 here, and I have x sub 1, x sub 2, x sub 3, and x sub 1 squared, x sub 2 squared, and x sub 3 squared, okay? Of course, this is not hard. You can really expand it. Might be even, it takes you less time because you don't need to think, you just expand and you can calculate. But let us assume that I want to go to higher dimensions with the same kind of pattern. I have 1, 1, 1, 1. I have 4 variables here, 4 variables squared, and 4 variables cubed. So we want to see if there is a pattern going on. So do you have any idea how can I row reduce it to an upper triangular matrix? The same idea. Do you remember what I told you? Focus on this one. Use this one to get rid of these one without even thinking about what is happening elsewhere. Okay? So you just take this one. How should I get rid of these two? So I copy and paste the first row without touching it. Okay, I want to get this row. What do I do? How should I get rid of this?
Add the negative one.
Negative of this one to this one. Again, you might think I am making this harder, but this algorithm doesn't care about what's happening elsewhere. The mathematicians have proven that the following this algorithm will always work. Okay? So if you just do that, this becomes 0. And then this becomes multiplied by a negative sign and added here, so it becomes x2 minus x1. And the same thing here, but the difference is that this becomes x sub 2 to the power of 2 minus x sub 1 to the power of 2. And I want to get rid of this one as well, so I will do the same thing. I multiply this by a minus sign and add it here. So then it becomes 0, x3 minus x1, and x3 squared minus x1 squared. Okay? Yeah, of course you can concentrate on this one and use this to get rid of that, but algebra becomes involved. Do you have any suggestions for me before getting rid of this using this? Simplify this a little bit so that the algebra is not that involved. For example, this combination x sub 2 minus x sub 1 and x sub 2 squared minus x sub 1 squared, what can I do with them? So what do you think I will write for this one? Instead of this one, what can I write? It's a very famous identity, isn't it? What can I write? Are you frozen? What can I write?
The conjugate?
Yes, the conjugate rule. But what is the goal of conjugate rule? Do you think there is a point to write the conjugate rule because it is a conjugate rule?
No.
In general, no. The answer is no. But here it's also helpful. Not only it is a conjugate rule, but it is helpful.
Okay.
Yes, how?
You can pull out x2 minus
Yeah,
x2.
you can factor this out. And then it becomes 1. So instead of working with this combination, you just work with 1. Okay? And I hope that you agree with me. The second one is also not only the conjugate rule, but also helpful. Oh, I made a mistake here. One of them is plus, sorry. Yes? So let us now momentarily forget about the algorithm, use the previous theorems 2 times. One on this row, I pull this one out. One on this row, I pull this one out. So what I get is x2 minus x1. Then I have x3 minus x1. Okay? And then what happens? I will have 1 x1, x1 squared, 0, 1, x2 plus x1. And then I have 0, 1, x3 plus x1. Okay, now I go back to my algorithm. I hope that you agree applying the algorithm on this is easier. So what I do, I focus here and I use this to get rid of this 1. So what should I do? I copy and paste whatever I have here. So it's x2 minus x1. And then I have x3 minus x1. And then I have 1 x1, x1 squared. And then I have 0, 1, x2 plus x1, and then if I do that, it becomes 0, and then this also becomes 0, but you have to calculate it in your head. Multiply this by minus sign and add it here. x1s will cancel out, you have x3 minus x2. Yes? Now, if I ask you what type of matrix, what type of determinant you are facing, it's clear this is the main diagonal, everything below that is 0. So this is an upper triangular determinant, so we don't need to expand it. So I copy and paste these two. And then I multiply these numbers. 1 times 1 times that one is just simply x3 minus x2. So that is the expansion of my determinant. This determinant becomes important if you want to find the best polynomial fitting some data. And this determinant is a famous one, which is called the Vandermonde determinant, okay? This is the name. And you can consider the most general case. So if you want to calculate this using the same methodology, you can show that this, after expansion, becomes this long product. So you start with x2 minus x1, but you start with x3 minus x2 minus x1, you start with x4 minus x3 minus x2 minus x1. So whenever you start with a variable, you have to subtract all previous ones and multiply them. So that is the general pattern. Of course, I don't know how much you're familiar with this symbol. This is something similar to sigma, but for product. So this means that you need to multiply these if I is less than j, j is less than or equal to n, I is greater than or equal to 1. This is a shorthand notation of writing this long product. Okay? Okay, so I will stop here, so we continue later. Any questions? Thank you.